All right, we're going to go remote today. And right now, if you're watching this video, you should have the review sheet in front of you. Also, I put it on Google Classroom. You can print that out. If you have that with you while you're watching the review, it really, really helps a lot. All right, let's take a little trip here. All right, is everybody ready? Now, if you want to move, you can, but I'll be doing things over here. See my goggles up there? Can you hand those to me? They're see, I think they're in that gray case. Yeah, thank you. All right, here we go. Are you ready? Let's find out. And you can pat yourself on the back if everything I say, not yet. Everything I say at the table, say, wow, I did figure that out ahead of time. I already knew he was going to say something like that. All right, so here we go. At this table, you started out with some copper. And so if you look at the top, what does this reaction have to do with things that we've learned in the past? All right, so let's take a piece of copper and we can heat it. Just like you did, and we made observations, but I'm thinking that something's supposed to happen here, but what is it that copper is going to react with? So if you had to write the balanced equation for this, what would you say? What do you have written down there? Even though you wrote on your lab report, did you? Can you tell me right now? So what is it? Copper plus what? Okay, so copper plus oxygen. Why don't I want you to do that? Look, there you go. Hey, go ahead and do it. Copper, go ahead. Go ahead. Why doesn't the copper react with the oxygen right now? Why do I have to heat it? You're going to say, because the direction said to heat it. But why? What do you think? Look right there. Activation energy. Energy that is added to get a reaction to start. We talked about that before, didn't we? It will react with oxygen, but not at this temperature. And so I have to put on here and provide it with some activation energy, and then I can get a reaction. And so what is it? Copper plus O2 in the air yields what? And you had to look this up. What is this black, silvery black material? What is that? And everybody here is supposed to know that. If you took the test today, you would not do well if you can't write it out. Copper plus O2 yields what? But which one? Which copper oxide? And you had to look it up, didn't you? So it would be copper 2 oxide. How do you write that? Okay, so let's write that down. And it says here, let's fill in the blanks, it says, why didn't copper react quickly with air? It needed activation energy provided from what? Where did it get the activation energy? From the flame, right. The copper will react with the O2 in the air to form CuO, which was what color? And I'll ask you on the test, what color was the copper 2 oxide? Everybody got that? Now, there was another thing we did, and I said do the, it's called the match thing. And one thing, even though it was accidental that a student did this one year, I asked everybody else to keep doing that. And what you had to do was you heat this up until it gets hot. And then you had to see whether or not it was hot enough to light a match. Okay, so yes, it is. So it's pretty hot. And it still is. But then you put it back in the flame, what do you see? Now, if you didn't see that, there's something wrong because I asked you to do the match thing, and so you should have seen that. Well, that adds a new little component now, and I'm going to teach you a little mini lesson. Some elements, when you heat them up and you excite them, electrons will absorb energy and give off light. And we call that a flame test. Now, the flame test, I'll show you one. Here's one. I put some copper sulfate. This is copper sulfate. So there are copper's in here, and I've been letting it soak overnight. I hope it's going to work. I think it is. Let's put some copper sulfate in the flame. What do you see? So there are some elements, especially metals. There are a lot of metals that when you heat them up and you get them excited, they identify themselves and said, hey, I'm copper. And copper gives off a green flame test. Here's another one. This one is potassium. I took some potassium nitrate, which is soluble, and I put it in a stick. The stick's been soaking it overnight. Because it's been soaking, it shouldn't catch the flame on fire, the stick. But what kind of flame test does that give? Can you see a color there at all? It's not as visible. Does anybody see a light purple? Like a really light lavender? That's not so easy to see. Anyway, potassium is known to give off a purple flame test. Here's one that, one of my favorites. This is lithium. I took some lithium chloride, I put some water in it, and what happens to lithium when you excite it? Ooh, okay. So lithium, I would use that for fireworks. If I wanted to have some fireworks that had different colors, I'd put some lithium chemicals in there, let the main explosion provide the activation energy, and you could actually get some colors like that. Here's another one. You can do this at home if you have a gas stove or something like that. I took some table salt. What is sodium? Does sodium give a flame test? And it does. And this one's usually bright orange. Yeah, they get bright yellowish. Everybody see that? So sodium is known to give off a yellow flame color. And here's one more. And this is strontium. And strontium is like lithium. Even though lithium is group 1, strontium is group 2, look what happens here. Strontium. Oh. Now that red's a little bit different than the other red, isn't it? That's kind of an orangish red. Can everybody see that? You want to see lithium again? I would. Okay, you want to see lithium again? Ooh, that's more of a scarlet red, isn't it? And so, and I didn't do all of them, I just did some of them, but I wanted you to know about flame test. And I had somebody, I don't know if it was from this class or not, but somebody took the nail. Remember over here, the nail got coated something on it, you know that? And they wanted to put that in the flame, and we did it one day. And guess what happened? It was green. So what do you think was on this nail over here? Copper. All right, what do you think? Questions about number 1. Now, let's take a look. And if you go up to the board, it says here, activation, we already did that. What kind of reaction was this? How would you classify this reaction? Let's see if I can hurry through all these. I may not get to all of them, but I'll try. All right, so what do we say here? Activation energy, it doesn't react quickly with air, and these activations are provided by the burner or the flame. Copper react with the O2 in the air to form, and which is kind of like, what do you say? What do you say, dark silver, gray? What do you call it? Dark, gray, silver. All right, what kind of reaction was this? Everybody? Okay, good. So we know that. And so, but if it's synthesis, you could also classify it as what? Redox. Okay, I'm sorry. So synthesis, but also is redox, isn't it? Now let's write out the regular equation: Cu plus O2 in the air in the presence of heat, and the heat's from the flame, and we'll make copper 2 oxide like that. Everybody got that? Is that what everybody had? And that'll be one of the questions on the test. Now you have to balance it. Okay, that didn't take too long. Everybody got it? So I'll ask you to write a balanced equation for that table number 1. Now let's do Leo and Ger, and I know that some of you didn't like this at the beginning, but you should see how easy it is now. It should get a lot easier for you now. Who lost negative electrons and became positively charged and got oxidized? Well, let's go over here and get some oxidation states here. Copper is 0, and oxygen is 0. And here copper is +2, oxygen -2. So who got oxidized? Who lost negative electrons and became more positive? Copper, okay? Now copper started at 0 and ended up as copper +2. Now how in the world did you do that? How'd you go from 0 and jump all the way up to +2? By getting rid of what? 2 negative electrons, isn't that right? Does that make more sense to you now? Now we need to fix the numbers because the balance equation said you didn't start with one of those, you started with what? 2. You didn't end up with one of those ions, you ended up with 2. And that means it must have been how many electrons? Is it a little easier now? Now who got GERD? And I bet, hey, there's only 2 things here, so let's do one oxygen at a time. Each oxygen started at 0, leave a space. And each oxygen ended up as -2. Hey, what happened to you, oxygen? You went from 0 and dropped all the way to -2. How did you do that? Well, I did what? I gained 2 negative electrons, didn't I? Now let's go back and fix the numbers. You start with 1O. No, I started with diatomic oxygen. So that means I need 4 electrons. And what about over here? What do they end up with? Didn't that end up with 2 of those oxygen ions? What do you think about that? All right. Special note, copper metal, if heated enough, can give off a what thing? I think your group, you had a small piece that was kind of like a little triangle. Did you get a green color without doing the match thing? Yeah, if you get little tiny pieces of copper on the edge or kind of jagged, you can sometimes get a green color without having to do the match thing. But I've never really looked into it. But that match, lighting on the copper, somehow must loosen. It must loosen some of the copper atoms from the metal, and that makes them more likely to give off the green color. But I've never really investigated what it is about the match that does that. Okay, any other flame tests, and what did you find out? What do you remember? Tell me when you remember. What's one you remember?
Potassium was light purple.
All right, so potassium was kind of light purple. What else?
Lithium was like red.
Yeah, that was real red, very red. And another one like it was strontium, which is kind of like an orange red. And what was the other one?
Sodium was yellow.
Yeah, sodium's really bright yellow. Okay, all right, let's go to reaction number 2, okay? Let's go to reaction number 2. This is hard to do with this camera and all that, but I'll do the best I can. For the people out here, I'll do the best I can. But, all right, now over here, even though this one wasn't super exciting, that didn't have to do with flames or anything like that, this is one of my favorite ones because we have this thing called a nail. And so what is a nail made out of? And you can buy aluminum nails. There are aluminum nails. They don't rust. And I sometimes buy aluminum nails if I want to put something outdoors and I don't want it to rust. But these are made out of what? Steel, aren't they? Now steel's an alloy, but the main component in steel is what element? Iron. So we said in the second one, what are the reactants? Well, iron is in the nail. And then what is this other stuff? What was this blue material? Here it is right here. What is this stuff here? Okay, copper 2 oxide, right? Copper 2 sulfate, I'm sorry. Now, so what happens is, even though it was kind of a quiet reaction, you were supposed to put this in there and then something happened. And in the lab report, you had to write what was happening. And a lot of you told me that the nail, what happened to the nail? Did it change at all? What do you remember? Gotta move on a little faster, okay? What do you remember? The nail, how many wrote down that the nail seemed to get fuzzy or looked like it was getting coated on something? You say something like that? Now, at the time, I doubt whether you knew what was going on. What was on the nail? I'm not sure. But if you were to come back to this about 20 minutes later, you would have noticed two things. You would have noticed the nail changing to kind of like a pinkish coral. Did somebody use the word coral? Salmon colored or whatever? Some of you would have said there's some kind of a salmon colored coating on the nail, and some of you actually tried to see if it would come off. Does this come off? Did it or not? It did. It does come off. But then if you came back 20 minutes later, you should have noticed something else. Now here's one that's been here a long, long time, too long. But what you would notice is that something happened in the nail, but something happened to the solution also. What happened to the solution? Raise your hand if you know real quickly. All right, what do you get? To what? So is it bluer, more blue, or less blue? Now that's the neat part. That's the neat part about this lab. There were two things that happened. The nail change seemed to have something coating on it, and the solution kind of lost its blue color over time. So let's see if we can figure that out. Look at the next reaction. What are the reactants? So what are the reactants? Let's try that. Table number 2, and I know that I'm going to do this all period. This is what we're doing today. But what were the reactants? Hurry up. Help me out here. Iron and what else? Okay, and it's called copper 2 sulfate, isn't it? It's not copper sulfate, it's copper 2 sulfate. And what kind of reaction is this? Let's write it out. Fe plus CuSO4. Now I'm going to be a little picky here. Watch this. The iron started out as a solid, didn't it? And what form did this start out as? What would you put after this? Now, if you're taking a lab test, you should know this. What form of copper 2 sulfate was this? Aqueous. And then what happened is you were left with two products, and one of them was FeSO4. And what was the other product? Copper. Now, if you take a look, what did you put after this one, and what did you put after this? I happen to know that copper was in the form of a solid. You know where? You know where I found it? Where did I find solid copper? On the nail. Some of you are so hung up on thinking that it was rust. Rust is a very orange material. That was not orange. It wasn't rust at all. It was pure copper. Okay, but what about this guy? What would you put after this? And it was AQ. If you look it up, you'll see that it dissolved in water. We never do see the iron 2 sulfate. We never do see it. It's aqueous. It's dissolved in water, isn't it? Now, how would you classify this one? John, help me out. Classify this real quickly. We've got to hurry. Everything we have to do is hurry.
Single replacement.
How much?
Single replacement.
Right. Very good. Single replacement. So, and how about balancing it? Did we balance it? Okay, now I want you to try to do the Leo Nagura without my help. All right, do it right now. And assign oxidation states. Okay. Once you assign oxidation states, you say, let's see, Leo, if you lose negative electrons, you become more, what? You become more positive. All right, so Madeline. Who got oxidized? And each iron started as 0, but it turned into iron that was +2. Say, how do you do that? How do you go from 0 to +2?
It loses 2 electrons.
Okay, everybody see that? Everybody okay on that? And the numbers are okay. And what about, Madeline, what about who got reduced?
The copper.
Which one?
The copper.
What about sulfate? It did. So it wasn't involved, was it? Sulfate was not involved. And this makes sense, doesn't it? If you're copper +2, so what happened when I put that nail in that solution, I didn't need any activation energy, did I? And what happens is that God made some elements like metals able to kick out other metals. And you can actually look up a list. They'll say, here's a list. If I'm above you, I can kick you out. And you can actually find a list, and it'll show you that iron can kick copper out of a solution. And so, what did iron have to do to kick copper out? Iron had to get rid of 2 of its electrons. And what did copper do? Copper was sitting around like an ion and said, hey, I'll grab a hold of those, and that'll turn me into neutral copper atoms. You get that? And so these are solid, aren't they? All right, so what changed color? The nail changed from what to what? Solution changed from what color to what color? See if you can fill that in. Even though it's called a review, you should be able to tell me ahead of time what these are. All right, Max, what you got? The nail changed from what to what?
So like silver. Silver to like orangish.
Orangish, okay. Copper colored? Or salmon colored, yes. And what about the solution?
It was like blue to like a lighter.
Right. Now, why? This is the hard question right there. And I'll tell you a situation. I've been to Yellowstone a couple times, and last time was probably, wow, it was almost 8 years ago. But they have these places called hot springs. Have you been to Yellowstone? Okay. Now, it's supposed to be water from the ground being heated by hot rocks underneath it, okay? The whole area is very thermally active. And so any water that's in the ground can be heated up quite a bit. You can die. You can actually die if you get into this hot water. Animals die all the time, and humans die sometimes. Some of this water gets trapped and builds up so much pressure underneath it, they form geysers. If they don't form geysers, they form mud pots. Bloop, bloop. You see those? Anyway, I've seen them where they have hot springs, and you have a little bridge that goes over the hot spring, and it's beautiful. And there are actually flowers and bacteria that can grow along the edge where it's not super hot, and that's pretty neat. And there are actually some bacteria that can handle that heat. But the water is incredibly blue, incredibly blue. There's no way that rainwater comes down as blue. What do you think? I think I have my own opinion. Why do you think that the hot spring water is blue there where there's a bridge? So if I go to another part of the park, the hot water is not blue. Any ideas? And I've been around long enough that I know humans a little bit better than you do. I could go to a mall, and if there was a fountain there with water running, what would I find at the bottom of the fountain? What do people like to do? If you go to Italy, if you take the Italy trip, and you go to the Trevi Fountain, what are you going to find at the bottom of that fountain? Coins. Now, what coins do you think might cause the water to turn blue?
Pennies.
What?
Copper.
Which ones?
Pennies.
Pennies. Now, so what is it? I want you to think about this. What was on the nail? Copper 0, right? And where did it come from? It came from here. Now, if you have copper, not metal, if I put copper metal in water, I'll probably see nothing. But what if I put copper metal like pennies in hot water that had other chemicals in it? Is it possible that there's some kind of reaction going on in that hot spring that might release some of the copper metal and change it into copper ions? And I think that's what's going on. Somehow, when you have copper ions in water, it looks blue. What if I had some copper chloride and I put it in water? What color would it be? What if I had copper 2 chloride? If I put it in water, you know what it would be? It'd be blue. Copper sulfate, blue. Copper nitrate, blue. This is why the solution was blue. Question, then why did it lose its blue color? Have you already figured this out? What? One more time.
The copper blood.
Someone say it again.
The copper blood.
What happened to my copper ions? If this is what makes it blue, then there must something happen to them. Go out.
Did they turn into copper metal?
That's right. And so when the copper ions that are blue change into metal, that's not blue. Copper and metal is not blue. And that's what I think is a kind of neat, kind of a quiet reaction, but it's one of my favorite because it kind of shows what's going on a little bit. And it's redox, isn't it? Okay, why do you steal wool? You ever think about that? And even though it's a very slow reaction, if I leave a nail, I got those nails out of my tool chest. If I have a nail that's been sitting there for a year, very, very slowly, you could get the oxygen from the air reacting with the nail a little bit, and you can get a coating, some kind of an oxide coating. So I want to get rid of that to get down to bare nail, and that's why you had to use the steel wool. Okay, now let's go to, let's talk about reaction 3 and 4, okay? Now, reaction 3 and 4, can you hand me, go ahead and hand me that real quickly. Give me the whole iPad there. I am going to tell you what happened, but wouldn't it be nice if everybody in this room today already knew? How many of you already know what happened at table 3 and 4? You think you figured it out? One person? Okay, 2? Because that was your job to try to figure this out. So let's go to it, ready? First of all, you've never seen in that whole chapter we had to write chemical formulas. Did we ever write anything that looked like that? No. These are special kinds of chemicals, and they're called hydrated crystals. Now, God made some ionic compounds that are called hydrated crystals. I could look up in a catalog for you, and I could show you something that was called blah, 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 trihydrate. This was, what's the name of that chemical? I'll ask you that tomorrow. What is the name of that chemical? And it's what? Copper 2 sulfate. Don't stop there. Penta. What's penta mean? 5. Pentahydrate. And that's actually part of the chemical. It's not copper 2 sulfate and water. It's not. It is a part of the crystal. And for every one of these, there are 5 waters locked up into that crystal. And it had hundreds and hundreds of those crystals, didn't we? And so what happened is, you put this stuff, and what happened to it? And that's a dot there. What color was this stuff? Everybody. It was kind of blue, wasn't it? Okay, now, so we put this, and why did I put it in the flame? Why did I do that? You guys got to give me some more, say something. It's just like table 1. What am I I'm trying to get this to react, right? So what do I have to do? Activation energy again, right? So if I provide activation energy, what kind of reaction is going to happen here? Everybody should know. Decomposition. Now, first time I did this, I don't know, 25 years ago, I wasn't certain about what the products were. I looked it up, just like you did. And so what you end up getting is this stuff, which is what color? What did you think it was? Kind of like gray white. What did you think? Is that what it was? Is it kind of like grayish white? Is that what you call it? Now, some of you heated it really too long. All I really wanted you to do is to change the color of it. But some of you like put it in the furnace, and then you might have gotten some yellow color. But what you were doing, you were actually breaking down the CuSO4, and sulfur gives you like a yellow color. So I really didn't want that to happen, but some of you got that, but that's okay. Now, did you have any evidence that water was one of the products? Really, if you remember that table, it had Pyrex, so we checked to see Pyrex. I started heating it. It starts changing color immediately. Which part changed first? The inside of the chemical or the outside? And very obvious. It was very obvious. If you heat it, did the inner part of the chemical change or the outer part? The outer, for sure, didn't it? And anyway, what happened is, there's no way you could have missed this huge amount of steam coming out of that test tube. And what's steam made out of? Water. And at the end, some of the steam at the top of the test tube, it was cool enough for some of the steam to change back into liquid water, wasn't it? There's no way you could have missed that. Now, what kind of reaction is this besides decomposition? Would you say it was exothermic or endothermic? Would the reaction itself give off heat, or did you have to put heat into it? So which one is it? Endothermic. And then you let it cool off, and the reason I wanted you to cool off, because some of you would not believe, if you didn't let it cool off, you wouldn't believe what happened here. And so you took this stuff, which was white, right? It was white, wasn't it? Gray white. And what did you add to it? What was it? Didn't you add water? Is that right? And then what happened? And some of you, it's not till today. Today's the first time you finally figured out that what was the product here? Copper 2 sulfate, pentahydro. Oh, the reaction table 3, I did the reverse. I reversed that reaction. This one changed from here to that, and you had to add energy. But what happened here? This was neat. When this reacted with water, it formed that. But what happened? What did it feel like? It was giving off. That's pretty neat. That's pretty neat. There's a reversible reaction there, very exothermic. Now, because I feel that hydrated crystals are very special, we don't really see it is decomposition. And what's this one called? This one is decomposition. What's this one? Synthesis. But because it's a special case, I don't see anybody really changing their charge, and so I'm not going to do, it should be redox, but I don't really see it, so it's kind of a special case. So hydrated crystals, that's why I don't have you write the half reactions there, okay? All right, let's do the next page. All right. On the next page, this was a table over there, and what you did is, and I will ask you, what were the two chemicals? See if you can tell me without looking it up. What were the two chemicals? And I know that was several days ago. What was this? Anybody?
Sodium chloride.
What is it?
Sodium chloride.
Say it one more time.
Sodium chloride.
No, I didn't start with that. What were the reactants at that table back there? It was sodium something. What was the other one? Calcium was another one. What was it? Sodium carbonate. All right. Now carbonate is -2 and sodium is +1. So there we go. Sodium carbonate, aqueous. And what did it react with? Yes. And this is +2. This is -1. That's why. See that? And then what happened? Did we get a reaction or not? All right. What kind of reaction was it? Double replacement, all right? Okay, now, so if double replacement, what are the products going to be? Somebody say it again? NaCl. Do you remember seeing that? Did you see NaCl? I believe, if you look on the chart, all sodium salts are what? So, no, you never saw that. You never saw the sodium chloride. If I didn't have a rule against tasting it, and I do, I could have put my finger in there and I would have tasted salt water. What's the other product? Calcium carbonate. And if you look on the chart, definitely. And what color was it? And what color was this? What color was the stuff that wasn't the precipitate? Clear. Hey, wait, what color was this? No, right here.
No, they were all clear except for the salt.
Except this one was white. Matter of fact, one of them that was left overnight, the precipitate eventually, because of gravity, went all the way down, and all of it was at the bottom. Now, I don't know if you knew this, but calcium chloride has some other names to it. It's called limestone. It's called chalk. It's called seashells. Seashells are made of this. Anyway, this is called calcium carbonate. All right, now let's go ahead. I'll give you 1 minute to do the Leo and Gur. Ready? Go. Let's see who can be first. Raise your hand as soon as you're done. Oh, they beat you. Just like they're going to beat you on the test. How did you beat them? How did you get that done in 1 second?
There are none.
Oh, darn. Wait a minute. You're supposed to know that. Double replacement. There's no redox in double replacement, is there? All right. All right, there we go. Next.
Rookie mistake.
All right, ready? That's right. And you're all rookies right now, but you're getting better, aren't you?
Yeah,
You're getting better.
We're the pros.
Okay. Now, let's go to the next table. Next table.
It's all you.
On the next table, go ahead and write out what you think happened here. Here, on Leo and Gur said, really? Really? Okay.
I'm gonna write rookie mistake.
All right, how about this one? Ready? You put a metal with an acid. That table there, you add a metal to an acid. I know you didn't study yet, but could you come up with the balanced equation right now? And the more of these you can come up with, you'll find the test to be very easy. Anybody know the metal back there? Zinc. Anybody know the name of the acid? Yes. And I'll put little symbols here. That was a solid. This was a liquid. And I should say aqueous. I'm sorry. Aqueous is solution. And what happened? I know one thing that happened. We got bubbles. And what do you think those bubbles were? Say it again. And why do I write H2? It's a diatomic element, isn't it? And that was a gas. And what was the other product?
Zinc chloride.
And everybody knows the zinc's an always metal plus 2 minus 1. And they're okay there? Now we'll balance it. Let's balance the equation. 2 chlorines, 1 chlorine. I can fix that. 2 hydrogens. Oh, yeah. I'm there. What do you think? Now, what do I put after this? I know what this looks like. It looks like bubbles. What does this look like? What does it look like? You never see it. You never see the zinc chloride. Why not? It's aqueous. Everybody got it? All right. What kind of reaction would you classify this as? You got to hurry a little bit. What is it?
Single replacement.
But if it's single replacement, it's also redox or not?
Yes.
All right, you do it. By yourself. You do each one of those, and I'll put the answer down. He said, oh, I'm getting better at this redox stuff. And if you have to leave, what you'll see is the rest of the video will show this one, okay? And so, and maybe you already know what's going to happen, but. All right, bye. All right, everybody good? Let's see. I bet. Ooh. Noah Ramos, you think you can do this? If I was in a state championship swimming team, I'd be able to do redox, wouldn't I? Just kidding, but let's go ahead. Who got more? If you lose negative electrons, you become more positive. Who got more positive? Zinc went from what? Go ahead, help me out here. Zinc had an oxidation state over here as what? 0. And what did it turn into? How much? How do you do that? Yes. Very good. Now, let's check the numbers. Did you really want to start with 1 zinc? Yes. Did you only end up with 1 zinc ion? Yes. Okay, so that's correct. Now, keep going. No, keep going. Help me out.
2 hydrogens.
Hydrogen? Why not chlorine?
Stays the same.
Yeah, nice. Very good. What did hydrogen start out as?
2.
What now?
0.
Did it? Is it by itself or is it in a compound? Ah, it wasn't 0 then. Isn't this -1 and this is +1? Isn't that hydrogen +1? Because that's -1. Okay, so each hydrogen, leave a space here, each hydrogen went from 1 to 0. Got that? All right, help me out, Noah. Did you really start with only one of those? And by the way, that would take 1 electron. You have to gain 1 electron, wouldn't you? But did you really start with one of those? How many?
It's 2 electrons.
Well, I had 2 hydrogen ions, didn't I? And that means I have to make this 2, and that's good because they have to match. How'd you end up at? Coefficient 2? Coefficient 2? Or is it in the form of diatomic hydrogen? See that? Does that work? And these match, don't they? That's good. All right. How did you know what the gas was? And what I'm going to ask you to do on the test, I'll say, explain how to test for hydrogen gas. Every year, I tell people not to do this, but every year, here's what happens. Well, you get a test tube, and you go get some hydrochloric acid, and you put some zinc in it, and you put your thumb. No, no, no. Don't do that. The whole space is only this big. I have people turning over the paper. They're telling me everything they did, and they said, and I blew my nose 3 times. No. When I say, what is the test for hydrogen gas, what do you say? Okay, you collect the gas, you got the gas, right? If you put a what? What's it called? If you put a what? A burning wood splint. If you put a burning wood splint into the gas, and if it does what? If it pops or explodes, then the gas was what? That's it. I didn't ask you how you made the hydrogen gas. I said, what is the test for hydrogen gas? Everybody see that? So, here's one I never asked you, but I will on the test. There were 2 reactions at that table. One of them was the pop test. Ready? I'll give you 1 minute to see if you can give me the balanced equation of the pop test. Raise your hand as soon as you got it. Wait, is that one of those trick questions again? All right, write out the balanced equation for the pop test. And raise your hand as soon as you get it. Still waiting. Anybody? All right, Tyler, what you got? Go.
I have 2 H2 plus O2
H2.
plus O2.
Okay,
Turns into H2.
that's right. And we know this was a gas, and we know this came from the air. And it just happened that this reaction is so powerful when it reacts. So much energy is given off that it actually makes the air expand so quickly. It breaks the sound barrier, and it's also so hot that we never do get to see the water because it's in the form of steam, isn't it? But if I could catch that and catch it on a cool surface, I could probably actually see it turn into liquid water. And then we have to balance this one. And 2 O's, 2 O's, there we go. Very good, what do you think? There was actually another reaction that took place at that table, wasn't there? That was called the pop test. All right, let's do number 7. And this one, in my opinion, and I only have 4 minutes, but I think this is the trickiest one of all. I think if you didn't look this up at all, you would have gotten tricked. So does anybody think they can tell me the balanced equation for this? All right, there you go, Noah.
2H2O2.
Give it to me without the coefficients first. What is it?
H2O2.
What's that called? What color was that? It was clear. It looked like water. Now what?
It yields H2O.
Yields, wait a minute. If you say yields right now, you're saying it's a decomposition reaction? I would too. Yields what?
H2O,
How do you know that?
produces condensation.
You saw the condensation? Maybe. But what, you know there was a gas produced though.
Well, it's meaning too.
Okay, now let's go ahead and balance it. What do you have here?
2H2O.
A 2 here?
Yep.
Okay, that gives you 4 oxygens. So I'll need 4 here. Uh-oh, wait a minute. That gives you 4 hydrogens. So that gives me 2 plus 2. That gives me the 4 oxygens. Is that what you had? Okay. And you left something out.
Over the arrow, I put changes manganese with 2.
What's the name of that?
Manganese oxide.
Which one? One of the companies called it manganese dioxide, didn't they? Normally, I wouldn't use that prefix method because it's metal, non-metal. What's the other name?
Manganese 2 dioxide.
Which one?
Manganese 2.
Which one? Each oxygen is -2. Each oxygen is -2, and I have 2 of them. That's -4. What's the other name? Yes, manganese 4 oxide, and the company called it also manganese what? Dioxide. Now, what were the reactants? There's only one. There was only one reactant. What were the products? There they are. This is a gas, wasn't it? And it says here, then what happened to the other material? And I put it over the arrow. You were correct. You put it over the arrow because what is it? Is it a reactant or a product? It's neither. You're right. It's a catalyst. Catalyst is a chemical that speeds up a reaction. It itself is not altered. What's in that big beaker back there, that waste beaker, that black stuff? What's the black stuff that's in that beaker right now? Anybody know? Jonathan, what do you think? What do you think's in that big beaker back there? Right, manganese dioxide. I can filter that out, use it again next year. It was not altered. Now, is this redox? Decomposition is redox, isn't it? Now, I'll tell you what, this is the trickiest one of all. This is the trickiest redox of all because let's take a look. What oxidation state would you give hydrogen right here? We have 1 minute to finish this. What oxidation state would you give hydrogen? It's in a compound. Hydrogen is always what? +1, right? Now, what about oxygen right here? Raise your hand if you know what oxygen is going to be here. Say it again. -1. I thought oxygen was always -2 in a compound. Except when? When we were learning to name compounds, oxygen is -2 in a compound, except when's the only time oxygen is not -2? When it's in a what? Peroxide. And this is hydrogen peroxide. So what's the oxidation state of oxygen in hydrogen peroxide? Whoa, it's only -1. -1. And what is it here? Hydrogen's +1, oxygen's -2 here. And this is 0. Whoa, this is weird. This is weird. So what do you think? If you had to do a Leo and Gurr, what do you see here? Who got more positive? And if I started with 4 hydrogens, I don't know how many, but I'm going to say half of them, maybe. 2 of the oxygens that were -1 would have done what? How'd they get more positive? Oh, sorry. And what about the other one? What about the other 2? Wow, that was the weirdest one. That was probably the weirdest redox you've ever seen, because some of the oxygens got reduced and some got oxidized. And one more thing, then we're gonna leave. How do you test for the gas? Please don't tell me how you made it. What's the test? Real quickly, we'll be finished. What is it? Flaming stick? I don't think so. Glowing. A glowing wood splint put in the gas does what? Relights. And that's always been the test for about 150 years for oxygen gas. Okay, thank you very much. And I have no idea exactly what's going to happen, but whether you take the test tomorrow or Friday or Monday, you can get ready, okay? Yes.
What about the safety rules?
What is it?
What about the safety rules?
Okay, what are safety rules that you didn't know before? When you heat glassware, you look for what name? Pyrex or Chemex. When you're heating a test tube, you never what? Point to anybody. Anybody, right? Anybody else? What else? Well, you don't. Yeah, you don't drink it. Well, is there a new one? We always had don't reach your hand over a flame, that kind of thing. Okay, that's good. That's good. That's good. All right, thank you.